Hi there, folks. Today we're looking at applying the standard normal distribution. And we've kind of dealt with two things here in terms of normal distribution. We've looked at normal distribution of data sets where we have the mean and we count out by the standard deviation. And from there, we've used things like the empirical rule to estimate certain values. We've also looked at the standard normal distribution, which is where we have a mean of 0 and it counts out by ones. And that's the kind where we use our z-chart in order to come up with values. We want to kind of merge those two ideas, all right? And so the idea here is we're going to convert normal distributions to the standard normal distribution. And it's really not a mind-blowing concept. We can take any normal distribution, so anything that's normally distributed, and we can convert it to the standard normal distribution just by changing everything to z-scores, okay? And so when we kind of look at this, the thing that we started with is we had like the mean in the center, and then we counted out by standard deviations. And those were the kind that we kind of used our empirical rule for, but that's all we can do with those is use the empirical rule, okay? What happens now is if we convert each of these values to a z-score, what happens if we think about the formula for a z-score? Remember, the z-score equals the data value minus the mean divided by the standard deviation, which we'll use that again today. If you think about converting like this center value here, the mean, if I were to convert that, now all of a sudden the data value is the mean, I would do mean minus the mean divided by the standard deviation. Well, that's going to be a 0, okay? And so really that converts to this middle value of the standard normal distribution. If I would convert each of those values that represent the standard deviations, I would simply get a 1 here, a 2 here, and a 3 here. A -1, a -2, and a -3, okay? And so again, this is not a real mind-blowing concept. If I take each value from the normal distribution, convert it to a z-score, now I have the standard normal distribution, okay? The advantage of this is basically if I have a value somewhere in the middle of this guy, like we know how to estimate like in between here is 68%, two standard deviations is 95, okay, those kind of things. But if I have a value that's somewhere in between here, maybe it's halfway in between these guys, and I want to come up with the area that's under all this, there's no way for me to do that in this format. But we've learned that I can calculate that value when I'm looking at the standard normal distribution because I can look at that value up on my z-chart. And so by converting whatever this value happens to be to a z-score, well, it gives me the value on the z in my z-chart, and now I can find that probability, that area underneath that percentage that's below that value, okay? So simply by converting everything to z-scores, now I'm dealing with the standard normal distribution, which I can look up on my z-chart, okay? For example, if I look at something like this guy, a class's scores are normally distributed with a mean of 78 and a standard deviation of 4.5. And so again, if I was looking at a normal distribution curve, I would have 78 in the middle, and then I would count out by 4.5s in each direction. But the fact of the matter is, I can easily convert this to the standard normal distribution. So instead of having that 78 in the middle right here, if I convert that score of 78 to a z-score, it becomes a 0, okay? The next value, instead of being, if I count it up, that would be an 82.5. If you convert that to a z-score, and we could actually run the calculations, do the 82.5 minus the 78 divided by 4.5, what's going to happen is I'm going to end up with just a 1 here, okay? And so everything's automatically converted to the standard normal distribution. So what happens is I just look at this value of 64 and say, hey, let's convert this to a z-score. So remember that my z-score is just the data value minus the mean divided by the standard deviation, okay? And I'm just going to plug that into my calculator. And when I do that, it gives me a negative 3.11. I'll just round it to 2 decimal places. And so basically that's telling me where to look on my z-chart to find this thing. So if I go to negative 3.11 on my z-chart, the z-chart gives me 0.0009, which is 0.09%. So in other words, the values that are less than that, according to my z-chart, is 0.09%. And that's it. All I had to do was convert this thing to a z-score, and now I can easily look up the percentage that's below this thing, okay? Same thing with the next guy. If I were to convert this 80 to a z-score, once again, I'm going to do z equals, it's the data value minus the mean divided by the standard deviation. And again, that's a job for my calculator. So I get 0.44, again, 2 decimal places. And again, I'm going to go look this up on my z-chart. And the z-chart this time reveals a percentage of 67%. It gave me 0.6700, so 67%, okay? And in fact, it did give me 67.00, so I could write it as 67.00% just to show the accuracy that came from my z-chart here. Although that 0.44 was rounded off to begin with, okay? The next one, same kind of thing. Now be careful this time. It says what percent of scores are greater than 70. Once again, I'm still going to convert that 70 to a z-score. And so I do 70 minus the mean divided by the standard deviation. That is a terrible looking decimal point. Let me try again. Again, I just plug that into my calculator. So I get negative 1.78. And now I look that up on my z-chart. However, when I look this up on the z-chart, this is going to give me the percent of data values below that score. So keep that in mind. So let me go take a look at the z-chart. And so the value from my z-chart is a 3.75%. Let me scoot that over a little bit. But again, that 3.75% represents the percent of data below that score. So if I want the percent of data greater than that score, I would do 100 minus that value, which gives me 96.25%. Okay, so I'm doing the same things that I've been doing, calculating those values from the z-chart, except I have one extra step before that, which is converting the data value to a z-score to begin with. Okay. If I look at the next one, same kind of thing. What percent scored greater than 85? So once again, I'm going to convert that 85 to a z-score. And once it's a z-score, now I'm talking about the standard normal distribution. Now I can look it up on my z-chart and go from there. So 85 minus the 78 divided by the 4.5. And again, this is a job for my calculator. So it looks like that gives me 1.56. And now I have a z-score 1.56. I'm going to look that up on my z-chart. Again, the z-chart will give me the data values below that, so I'll have to subtract it from 100. So let me go look it up. So it looks like the z-chart gives me a 94.06%. But again, that is the percent of data values below that z-score. So if I want above that z-score, I have to do 100 minus that value. And that gives me 5.94% above that z-score. Okay. Next one, what percent scored between an 80 and a 90? And so for this one, because it's giving me 2 scores, I have to calculate each of these as a z-score. So I'm going to do each of these. So I'm going to do z equals, let's see, I'm going to do the 80 minus the 78 divided by the 4.5. I'm also going to convert that 90 to a z-score, so 90 minus the 78 divided by the 4.5. Because again, I want each of these in terms of the standard normal distribution, because the standard normal distribution I can look up on the z-chart. So let me plug each of these into the calculator. So this one I get 0.44. I actually just did that one not too long ago. And this one I get 2.67. And so once again, I want the values between those two scores. So when I look each of these up on the z-chart, remember it's going to give me the data values below. And again, this one, sometimes it helps to draw the visual. So on this one, I'm going to find the data values below that 2.67 and then the 0.44. Just to remind us what we're doing with these things. If I have the data values that are below this guy, and then I also have the data values that are below this guy, if I want just the area in between these two, I have to subtract those two values after I find them. So just a reminder of what we have to do when we're looking for the values in between. So let me look up those z-scores on the z-chart, and then we can go ahead and subtract those. All right, so as I calculate these, this guy yields a percentage of 99.62%. This one reveals a value of 67.00%. And so again, if I want the amount of area in between those two, I have to subtract those, and when I subtract, I get 62%. Okay, so again, I'm doing the same things that I've been doing with my Z chart, looking up those Z scores and subtracting where I have to. The big difference is I have to convert these to Z scores first. Okay, so there's one extra step when we apply these standard normal distributions. If I look at something like this guy, really the key to an example like this, it says the height of a group is normally distributed with a mean of 5 feet 9 inches and a standard deviation of 6 inches. The thing that's going to make this a lot easier is if I kind of ignore the feet and inches and just do everything in terms of inches this time. Okay, so if I take this guy, 5 foot 9 inches is actually, let me write it off to the side here, 69 inches. Okay, I don't know why I wrote percent there like a crazy person. 69 inches. There we go. I'll use that uh, um, notation for this thing. But that makes all of this just a lot easier. Same thing like with each of these examples. If I take this first guy, that is 72 inches. Okay. So as I look at this first value says what percent would be less than 6 feet tall. In other words, what percent would be less than 72 inches? This is going to make it a lot easier because as soon as I go to do the Z score here, when I try to do the Z score, I want to do the data value minus the mean divided by the standard deviation. Well, it becomes really tricky when I'm subtracting things that are in feet and inches. A lot easier to do the subtraction. Plus, I'm dividing by a value that's clearly in inches. And so it really just doesn't work to keep these things in feet and inches. So if you run into examples like this, convert it to inches, purely inches first. Okay. So this one, data value 72 minus the mean, which is 69, over the standard deviation, which was 6 inches. And again, I plug this into my calculator, and it gives me 0.5. I'm going to write it as 0.5 is 0, even though the calculator didn't give me that 0. But that's what I'm really looking up on my Z chart is the 0.50. So let me take a look at the Z chart. And the Z chart yields a percentage of 69.15%. And that represents the amount below that data value. And it asked me what percent would be less than. And so that's the value I want. There's no other subtraction or any other operations I have to do. The Z chart gives me exactly what I want right out of the gate. Okay. If I look at the next one, same kind of thing. Again, convert this guy. If I convert that simply to inches, that's going to be 60 inches for 5 feet. And so once again, I'm going to convert this. So I've got Z equals data value minus the mean divided by the standard deviation. Okay. And when I do that, again, plug it into my calculator, that gives me a 1.5. And again, I'm going to write that as 1.5 is 0 because that's what I'm going to look up on my Z chart. So let's take a look at the Z chart. And so for my Z chart, and this was actually a negative, oh, I don't like the way I just squeezed that in there, negative 1.50. And when I looked at negative 1.50 up on the Z chart, it gave me 6.68%. And again, that 6.68% represents all the percent of data below that value. And it did ask what percent would be less than the 5 feet tall. So that is the value that I'm looking for. Okay. Next one, same kind of thing. Let's convert this first. 6 feet 4 inches would actually be 76 inches. Okay, 6 feet is 72 plus another 4 inches. And so let's convert that in terms of a Z score. Data value minus the mean divided by the standard deviation. And again, I'm just going to plug that in my calculator. And I get 1.17 approximately. And now I look that up on my Z chart. Z chart reveals a value of 87.90%. Again, that represents the data that's less than that Z value. Because I want to be greater than that Z value this time, I have to do 100 minus that value. And so when I subtract those, I get 12.10%. Okay. Next one, converting this guy. Once again, just convert this thing to inches, make life a lot easier on us. And so in inches, that's a 62 inches. 5 feet is 60 inches, plus the extra 2 inches, that's 62 inches. And now let's convert that to a Z score. So data value minus the mean divided by the standard deviation. And what I get this time is I get a negative 1.17, which I can go ahead and look up on my z-chart. The z-chart this time is going to give me a 12.10%. And again, that is the values below that data value. So if I want above that data value, I'm going to do 100% minus that value, which gives me an 87.90%. And I like these two examples back to back because if you haven't noticed it by now, this idea of symmetry within the normal distribution curve and within the standard normal distribution, hopefully you can start to see the relationship between the previous example and this example. And this idea that when I have the positive version of this thing, I got the 12.1. And when I have the negative version of this thing, I got the other half of that, which is the 87.90. Okay, so just something to think about. Some of you might be able to find some shortcuts within some of these instead of having to subtract from the 100 each time, that kind of stuff. So just something to think about. All right, last example, I'm going to convert each of these. So I'm going to convert this guy, the 4 feet 10 inches, that's going to be 58 inches. And here the 5 feet 10 inches is going to give me a 70 inches. And once again, I'm going to convert each of these to a z-score. So data value minus the mean divided by the standard deviation. For this one, also data value minus the mean divided by the standard deviation. So here I get a negative 1.83. Here I get a 0.17. And now from here, I'm just going to go ahead and look these up on my z-chart. And so when I look these up, this one from my z-chart yields a 3.36%. This one yields a value of 56.75%. And again, if I want the data, the amount of data in between, I simply subtract those. So I do the 56.75 minus the 3.36, and that yields 53.39%. Again, it's the same thing that we've been doing with these z values and finding the percentages from the z-chart, but we simply have that first step, that first extra step of converting these to z-scores for any standard, for any normal distribution. It now becomes the standard normal distribution, which I can look up on the z-chart. Okay.